Hi, welcome to my talk titled Nonlinear Observers, Precursor for Controlling Noisy Real-World Systems. So this is part of the IEEE Vancouver section, and this is the talk I've given on in UBC campus. To give a quick background, my current research primarily falls within the area of nonlinear controls with particular focus on alternate energy systems. So we're mainly looking at fault diagnostics, sensorless controls, fault-tolerant control, a wide class of nonlinear systems using nonlinear observers, and we're applying this to modeling and fault detection in fuel cells. My secondary area of research is on co-design, which is integrated physical system and control system design optimization of renewable energy systems. In here, we're looking at smart microgrid optimization and design of operational point, which is kind of the control, as well as physical design of an external axis wind turbine as well as vertical axis wind turbine. I'd like to thank partners and funding agencies, governmental NSERC, CFI, MITAX, as well as several industrial partners like Ballard, XP Power, Endurance, Surrey Fluid Power, DCD, Plastic to Fuel, and AgriChar, and few other partners who we have actually started working on and in the process of finalizing some of the partnership agreements. I'd also like to acknowledge the contributions of several students in the area of control. Amir Bailubiji, who completed his master's, Sagar Mehta, Ahmed Raza, who just started his PhD, Martina, who's going to be joining us in fall, so she's already started working on some of the stuff, as well as in the area of fuel cell diagnostics, Sasan, Babak, whose PhDs are in progress, in the area of co-design, Farad Ismail, whose master's was completed, Sunjita, and Pablo, who is actually a fellowship from Ecuador, who has a fellowship from Ecuador, Philip, who's a MITAX Global Research Intern, whose work I've been really impressed with, as well as Seth, whose MSc is in progress. In addition, I would like to acknowledge several multiple undergrad, capstone, and co-op students in all of these research areas. Coming back, so I would like to spend a few minutes talking about my secondary research area, which is co-design. So for the first, one of the things we're working on is we're working with a company to optimize the wind turbine design as well as the optimal operation point. So we did some simulations. So since we have some conflicting objectives of minimizing the response time as well as maximizing the power, we use something known as a Pareto surface, which allows us to pick a compromise design. So this is actually both the controller and the physical system optimization. So we did CFD simulations using OpenFOAM. Moving on, so we actually also focus on fuel cell diagnostics. So we're going to talk a little bit about this area as well. So in the area of fuel cell diagnostics, a fuel cell is actually made up of something known as MEA, or membrane electrode assembly, and this is where all the concept reactants react. What happens is when one of the cell actually leaks, so these are actually connected in a stack. When one of the cell leak, basically hydrogen goes from here, the anode channel, to the cathode channel, so there is usually a leak here, and then it consumes the oxygen, and the fuel cell actually becomes oxygen starved, and this actually causes additional problems. So the fuel cell might short, and there is issue with hydrogen emission. So we actually developed a model which can capture both the dynamic transient behavior of the fuel cell as well as the emission when the leak actually initiates. We actually experimentally validated this. We did the steady state as well as transient simulation, and we were able to capture both the hydrogen emission as well as voltage. So this is actually a transient simulation, so where we gave it different hydrogen leakages over time, and then you can notice that you're actually able to simulate this very nicely. And what we're working on is actually controlling, including some of the observer stuff into actually diagnosing the inception of leaks. So this talk is going to be more on the primary area, which in the area of nonlinear observers, and we'll see how we can do fault diagnostics, sensorless control, and fault tolerant control of a wide class of nonlinear systems. So before I kind of proceed too much further, I would like to give a quick background on observers. So we begin by considering a fairly complicated physical system. So anytime you have a system, you can decide on the different parameters as well as the different states, which are the internal variables of the system, and then write a dynamic equation in this form where U is going to be the input. In this case, it could be the fuel going into the engine, and then you're going to have output Y. In this case, it would be the thrust produced by the engine. The actual relation between the fuel going in and the thrust is going to be a nonlinear relation, which is going to depend on the internal states. For instance, the RPM of the compressor, as well as if this is going to be a part of an aircraft, it's also going to be affected by the velocity of the aircraft, which affects the inlet condition, and then that's going to decide on the actual thrust that's coming out. And what you would like to do is kind of control the thrust to some particular thrust set point by controlling the fuel. So you might have a control system which looks like this, and it would have a reference. Either you're going to measure the thrust and feedback or do something of that sort, or you might want to control maybe the fuel consumption for some reason. In which case you can basically decide on a control system which is going to take the x's, which are the states of the system, and then decides on the input that goes into the system. Unfortunately, not all of these states in the system are going to be known. What you would do rather is you're going to construct something known as an observer, which kind of tries to replicate the states of the system by considering the input U, which is going into the actual physical model, as well as the output produced in the system, and then you're going to have a model which is going to have an internal representation of the system, as well as some measure of the Y, which is the actual output, minus h of x hat, which will be kind of the output of your observer, and then based on that it's going to decide and then try to recreate the states. And what you then do is, once you have this x hat, you replace your control signal. Instead of using it as k, some function of x, you do it as a function of x hat. For this to work, you can basically just consider the ignore the controller part, because the controller is going to be common between the system and the observer. And then what you can do is try to figure out what does it take for the whole system to work. And then notice that for the observer to be of any use, we need the x hat, which are the estimates, to converge to x, which are the actual states of the system, irrespective of your initial conditions. So x of 0 and x hat of 0 are going to be the initial conditions of your system. Irrespective of what those values are, when you start your observer, you want the observer values to converge to the actual states of the system. So this was the objective when you're dealing with observers. You can think of an observer for a linear system as well. For a linear system, you have x dot is ax plus bu, and then the output y is cx. A, b, c are going to be matrices of appropriate dimension. And then what you can quickly do is actually construct, basically just using the model of the system, you can construct your observer as shown below, as x hat dot is going to be a x hat plus bu, which if you notice kind of mirrors what the system is. But now that you have the actual physical measurement from the system, you add an additional term, L times y minus c x hat, which is going to kind of be a measure of how much the observer sensor value is going to deviate from the actual sensor value. And then based on that, you try to kind of guide your observer towards the actual system value. You can define the estimation error as x tilde as x minus x hat, and calling that x hat converges to x is the same as saying x tilde should converge to 0. We want to actually construct a dynamic equation for x tilde dot. We can basically treat or consider what it actually means and substitute for x dot and x hat dot, and then when you kind of like cancel this term out, b times u being common can be cancelled out. You end up with x tilde dot is a minus lc times x tilde. Here L is going to be the observer gain, and if AC, the A being the system matrix, C being the observation, is observable, there is always an L that stabilizes. Indeed, you can actually arbitrarily place the poles of the A minus LC. So if you consider a simple spring mass example here, you can use MATLAB pole placement tool, which is place A transpose C transpose P, and then you take the whole transpose of it to place the observer poles at an arbitrary location. The reason you have the transpose here is that the pole placement is ideally actually designed for controller pole placement, but because the observer and the controller are analogs of each other, you can basically take the transpose of the observer and then you can actually use it to place the poles of the observer system. So if, for instance, you wanted to place the poles at -25 and -30, you can actually throw the whole thing into the pole placement tool, and then it gives you a gain of 50 and 490. Generally, when you want to look or study the stability of a system, we look at something known as the LYAPUNOV function. Traditionally, what we do is we choose a positive quadratic candidate function. The traditional quadratic is what is more traditional. The reason is you can actually write it as inner product, and you can basically use a lot of matrix manipulation here. So we start with B is x tilde transpose P x tilde. We want to ensure that P is greater than 0. This ensures that B, the LYAPUNOV function, is positive for all values of x tilde. And then we would like to show or kind of design an L or choose an L which ensures B dot, which is going to be x tilde transpose P x tilde dot, and then its transpose is less than 0 for all of x tilde not equal to 0. Now if you recall, x tilde dot is A minus LC x tilde, excuse me. If you plug that into the system, you basically get B dot is A minus LC P plus A minus LC transpose P and then x tilde. If A minus LC is Hurwitz or has negative eigenvalues, you can always find a P which basically ensures that V dot is less than 0. Now we actually look at a nonlinear system wherein we're going to look at a specific class known as additive nonlinear system. Here our f of x u is going to be a of x that we saw from before in the linear system, but then we have an additive nonlinearity in the form e times phi of u comma x or x comma u, and then we're going to add the plus bu, which is the actual output, actual input to the system, and then y is the sensor measurement. This kind of nonlinearity is fairly common in many physical systems, particularly in robotics, where your gravity shows up as a sine term, and a lot of other systems, when you actually do feedback linearization, actually shows up in this form. So this structure of the additive nonlinearity is fairly common in control system, and so we're not actually restricting our observer design. The observer is going to be x hat dot is a x hat. Essentially, we are again copying the system down, plus phi of u comma x hat plus bu, and then again as before we add our linear feedback term. The observer design term the observer design process is fairly complicated, and you can't really do too much beyond actually adding a linear feedback term. So you can potentially add a feedback term into the nonlinearity, but when you actually write up all the equations, we end up kind of we don't actually have any additional degrees of freedom. The estimation error, again we define x tilde as x minus x hat, and then phi tilde is the error in the nonlinearity, and then when we look at x tilde dot, it becomes a minus lc x tilde, and then this term over here, e phi of x and then e phi of x hat, that shows up over here. Now the question is, can I make a minus lc stable and then ensure that the x tilde dot actually converges to 0? So obviously this is going to be a trick question, and then we see that this is not actually possible. So if we look up LYAPUNOV function, so again as before, we choose a positive quadratic LYAPUNOV function. We take the derivative, and now that x tilde dot is a minus lc plus e phi tilde, we substitute that in, and then notice that we have two terms here. So we have our A minus LCP plus A minus LC transpose P term, and then we have a new term over here. So we'll notice that since we can place if AC is observable, the term here can be made negative by kind of choosing the L gain appropriately. Unfortunately, the term on the right side could potentially be a problem because the phi tilde can be all over the place, and you can't actually ensure that the phi tilde E transpose P and then X tilde is always negative. So to actually kind of illustrate this, we'll look at a very simple example. We are going to look at something known as a dissipative system, or kind of where your nonlinearity is always opposite to the X tilde term. So you can think of terms, you can think of the viscous drag, which is a dissipative system. Essentially, the nonlinearity removes energy from the system. And if you notice, I have made the A minus LC over here to have eigenvalues at minus 0.5 and then plus minus 2.3979 I. So the A minus LC part, the linear part of my system and observer, is actually stable. Now my nonlinearity, if you look at this over here, this actually is negative. So kind of looking, or if you think about the system physically, it looks like the system should be stable, right? So you have a linear part which is stable, and then you're kind of like throwing in a nonlinearity, which kind of just removes the energy from the system, and then you're like, okay, this should actually be stable. So what is happening here? So if you actually look at the Jacobian of the system, where Jacobian is kind of the derivative here with respect to the states here, x1 tilde and x2 tilde, and you'll actually notice that for x2 equal to 0 and x2 tilde greater than square root of 6, the eigenvalues of the Jacobian, or basically kind of the derivative of this term, is actually positive, which is actually really bad from a stability point of view. Again, I chose the value of x2 equal to 0 and x2 tilde greater than square root of 6 just to make things easier. You'd actually notice that if you plug different values of x2, you would get a different set of x2 tilde, which would basically make the system unstable. But long story short, even though the system itself is dissipative and you would expect it to be stable, the system is not stable. And indeed, because the Jacobian is actually positive, you can kind of, if you actually try to do the LYAPUNOV analysis, you would notice that the LYAPUNOV candidate function V naught will become greater than 0 when x2 tilde is greater than square root of 6. Hence, even for a dissipative system where you would think that nonlinearity actually aids in the stability of the system, you cannot really easily design an observer or kind of like arbitrarily choose the value of the gain, observer gain L. So in addition to that, we are looking at other challenges. In the real world system, we're going to have a sensor noise, which is going to be kind of an additive noise on the output. And then you could potentially have other disturbances acting or kind of affecting the system. Obviously, we don't have any knowledge of the actual values of the noise V and the disturbance W, and so that doesn't go into the observer. So what we do is we would have a nonlinear system which kind of looks as kind of, again, we look at the additive nonlinearity here. So you have this term FW added here and this noise nu added to the sensor value. So now we have additional things we want to kind of consider when you're actually designing the observer. So essentially, how do I kind of make sure that the system doesn't blow up or doesn't produce like really bad results when you have these noises and sensor noise and input disturbance. So what we're proposing here is we're going to design the whole thing for something known as a Generalized Sector Bounded Nonlinearity, GSB for short, and the nonlinearity is defined such that phi is assumed to lie inside a hyperboloid defined by, for all x comma x hat, there exists gamma 1 and gamma 2 in the real plane for such that for x tilde defined as x minus x hat and phi tilde defined as phi of u comma x minus phi of u comma x hat, we have phi tilde transpose phi plus gamma 1 minus gamma 2 phi tilde transpose g phi g x minus gamma 1 gamma 2 x transpose x tilde transpose g x tilde is less than 0, or you can potentially write it as in the quadratic form as minus gamma 1 x tilde transpose g x tilde is less than x tilde transpose g phi, which is in less than gamma 2 x tilde transpose g x tilde. Obviously this was a mouthful to actually describe, so let's look at a graphical representation of the nonlinearity. So essentially imagine you have an arbitrary nonlinearity, so you have the gx on the x-axis and the value of the nonlinearity in the y-axis. So what this basically means is the whole nonlinearity actually lies within gamma 1 and gamma 2. Again, because we are defining it as difference between any 2 points, we want to ensure that any 2 points of the system is actually bounded between the slopes gamma 1 and gamma 2. So essentially if I did a sweep, I want to ensure that the whole nonlinearity, all of the slopes everywhere, so you basically start with any x and any x1 kind of is bounded, remains bounded here. So essentially every 2 point on the curve is bounded by a sector here. So the GSB, the Generalized Sector Bounded Nonlinearity, actually represents a very general class of nonlinear systems. So for instance, if I said gamma 1 equal to gamma 2 equal to gamma, we actually end up with results for Jacobian nonlinearity, bounded Jacobian nonlinearity. If I further set G equal to I, this is basically the standard Lipschitz nonlinear condition that we see all over the place. If I set G equal to minus I and then gamma 2 equal to 0 and take the limit gamma 1 to infinity, we get phi tilde transpose x tilde is greater than 0. This is a non-decreasing nonlinearity. To kind of simulate a dissipative system, you can basically set some phi tilde transpose g x tilde is less than 0, for which we would set gamma 2 to 0, and then we can potentially set g to I and then take the limit as gamma 1 to infinity. So essentially, if you go back here, based on how we choose the value of how the nonlinearity is, you can potentially choose the different values of gamma 1, gamma 2 and g. So this basically covers pretty much any general nonlinearity we can think of. So the first step is, if we have this generalized sector bounded nonlinearity, how do I design an observer in the absence of noise? So this is the very first step. So we basically say that we design, if we can find a p greater than 0 and an epsilon 1 greater than 0, an arbitrary X matrix of an appropriate size such that the matrix M11, M12, M12 transpose minus epsilon 1i is less than 0, where M11 is going to be my A transpose P plus PA minus XC minus C transpose X plus epsilon 1, gamma 2, G transpose G, and my M12 is going to be PE minus epsilon 1 over 2 times gamma 1 minus gamma 2 G transpose. Once you can basically calculate these values, plug this into the matrix here, and kind of find a P and an X, which ensures that this matrix is less than 0. Then what you can do is actually choose L equal to P inverse X, and our observer will be stable. And the actual observer gain, because if you notice here, the unknowns P and the unknown X are linear terms, we can use what's known as LMI, linear matrix inequality solvers, in MATLAB or similar software, and then very quickly actually solve the observer design problem and then calculate the value of the observer gain, which will stabilize the system. Since this is an IEEE talk, I wanted to give a sketch of the proof. So we choose, or we start with the quadratic LYAPUNOV candidate function. V is x tilde transpose p x tilde. We try to take the derivative because my x tilde dot is a minus lc x tilde plus e phi. We plug this in, this is the equation we get. We have x tilde transpose x, and then you have this matrix over here, and then you have the effect of the nonlinearity showing up here. We replace PL with X because P is so if your system state is going to system is of size n, P is going to be an arbitrary n by n matrix, and L is going to be n by ny, where ny would be the number of sensors. So X is actually an arbitrary full matrix. So anytime you can solve for the value of X, so if you multiply X by P inverse, you can actually get the value of L. So this substitution is actually good. What this substitution allows us to do is to convert our nonlinear function. So if you look at this here, you're multiplying P and L, which doesn't really agree with LMI solvers. We're basically replacing the whole thing by a linear unknown. Then we use lemma, which is really nice, which is called an S procedure lemma, which basically states that if you have a arbitrary function v1 is less than 0, if and only if, this is important, so if and only if there exists a positive semi-definite function v2, basically v2 less than or equal to 0, and an epsilon greater than 0 such that v1 minus epsilon times v2 is less than 0. So here is the thing, so we're basically having a positive definite function here, we have a negative definite function here, which you're trying to show is negative definite. We're basically saying that, okay, so what I'm basically doing is I want to find a small epsilon here, such that if I kind of like remove here, so if I do v1 minus epsilon times v2, so notice that since v2 is negative, this is a small positive term that you're adding to here. So if this is less than 0, that means if I remove a small positive term here, that kind of, because you can potentially take epsilon down to 0, this kind of matches out. And in this particular case, we'd use v1 equal to v dot, and v2 is our relation that the nonlinearity satisfies, which is phi tilde transpose phi tilde plus gamma 1 minus gamma 2 phi tilde transpose g x tilde minus gamma 1 gamma 2 x tilde transpose g transpose g x tilde. So what this does is we're basically having a relation here. This term here is going to be quadratic in x tilde, and then this term here, what you're doing is we have the quadratic in phi tilde, and so we're basically going to write bigger v dot gets replaced by a matrix which is quadratic in x tilde transpose x tilde and phi tilde, and what we can do is basically write the matrix out, remove the x tilde and phi tilde, and then we can basically write the matrix equation, which will give the equation on the previous page. So let's look at the case where we actually have noise in the system. So notice that you can't actually use a LYAPUNOV stability in this case, because if I start with a quadratic LYAPUNOV over here, if I do the v dot, I end up with this term over here, which is 2 x tilde transpose p times f w plus l nu. Even if you have a bound, so if say w and nu are Gaussian noises, you can potentially have these to be completely unbounded, so you can't ever ensure that v dot is always less than 0. So that basically kind of means that you can't actually show or establish LYAPUNOV stability, or establish stability from a LYAPUNOV sense. Instead, what we do is we define or can try to create an H infinity observer. So the H infinity observer is slightly different. So what we do is, rather than try to show that the system is stable, we try to show that the system can be designed to achieve some kind of a minimized cost function, or satisfy a minimized cost. So the cost itself is going to be a ratio of two terms. So the numerator is going to be the some norm of my error, or estimation error, and then you basically divide that by the norm of the disturbance and a norm of the noise. So you kind of have a weighting function here, So W would be kind of like arbitrarily decided based on what your application is. So if you're really interested only in states 1 and 2, you can basically have the W weighted more heavily towards the states you're interested in. So what this does is, if I have a large disturbance, I'm not really penalized. I'm trying to do the best I can. So for instance, if I'm basically going for an exam, I've only been taught like 50% of the course. So what I'm basically trying to do is I'm trying to optimize my score based on the knowledge that I'm kind of have a limitation of the external noise, and then I'm trying to minimize or kind of design the best observer given that I have a limitation of the noise, or kind of the knowing the effect of the noise. So to put it formally, so we're basically saying that we would guarantee h to infinity performance given by 0 to some time, and then you have the numerator, which is x tilde transpose w x tilde, and so that's an integral divided by the integral of the weighted noise terms. So we want to ensure this is less than some 1 over rho after sufficiently large time. And so we basically say this is possible if and only if there exists an epsilon 1 greater than 0, p greater than 0, such that you have this matrix here, n11, n12, pf. The second row is n12 transpose minus epsilon 1 I, 0, and the last row is f transpose p, 0 minus q inverse, where my n11 is going to be rho w plus a transpose p plus pa plus epsilon 1 gamma 2 g transpose g minus c transpose r inverse c. My n12 is pe minus epsilon 1 over 2 gamma 1 minus gamma 2 g transpose. So this looks very similar to the observer we had before with the noise free case. So essentially, because it was noise free, you would arbitrarily choose the gain, but if you wanted to optimize for the effect of the sensor noise, you end up with the term minus c inverse c transpose r inverse c over here, and the other term that shows up is this column and this row over here, which is the effect of the input disturbance. So again, if we wanted to give the sketch of the proof, what we do is rewrite the cost function as a linear term rather than a ratio, and then we define an augmented cost function using the state equation constraint over here, basically j1 and then integral, and then you have this Lagrange multiplier over here, and we again use the reciprocity lemma and then define augmented function j bar, which is going to be the augmented function minus epsilon times v2, and then we minimize j bar and then write this result as a matrix equation. A lot of math. So we're going to look at a few illustrative examples here. So we look at a simplified version of a chaos nonlinear circuit. So we look at the circuit here. So it basically has kind of an diode on one side and the resistor. So what happens is you're going to have, if the current is positive, so you're going to have the parallel resistance over here less the nonlinear term due to the diode over here, and then if the current is going negative, the current only flows through RD here, RD2. So the whole thing here represents a nonlinear resistance. So the output is going to be the charge on the C1. So if I define my states as Q1, the charge in the capacitor 1, Q2, charge in 2, and the current, we can basically write the state space equation as follows. And then for the representative values of C1, L, RD1, RD2, and diode parameters, V0 is 26 milliamps, and the current here, we can basically kind of simulate the observer for this particular system. We need to choose some arbitrary values of the noise here. So we do that. So notice that we start our x hats at 0, and we kind of very quickly converge to the actual states over here. So we look at the cost function j, which is, we wanted to achieve j less than 0.1, so we're able to actually achieve that. Next, we actually look at extending the observer design method to observer-based fault detection. So again, we have the same system equation over here, and then what we do is we add either mu, which is an unknown term, b dx, which is kind of the parameter, and then based on the variation, which would be additive parameter, or we can have multiple unknown parameters. So essentially what happens is, this is kind of, if you might be having a system where you're not 100% sure about the mass or 100% sure about the dissipativeness. So what you do in this case, you can actually write the whole thing in this form over here. So where your uncertainty in your parameter is going to show up in this mu, and then how the uncertainty actually affects your state equation is going to show up in this b times d term. You can similarly have additional bias and gain faults on the sensors, and so we basically extend this to make an adaptive sensor, adaptive observer, which can kind of estimate all of these parameters. So again, in this case, just to kind of illustrate, so you have an uncertainty in the mass 2, which basically shows up as follows over here. So once again, we notice that the actual and estimated parameter, so basically both the states converge, and we actually notice that the simulation is 35% faster than an extended Kalman filter. So we'll actually talk really quickly about what extended Kalman filter is in a couple of slides. So we also notice that the adaptive parameter estimation also converges. So we're going to compare the system to the extended Kalman filter. So extended Kalman filter, EKF, is an extension of the Kalman filter to nonlinear system. So Kalman filter is essentially kind of the gold standard when you want to optimally reject noise and make an optimal estimation of the system. So the nonlinearity equation we write in terms of F and L, and then the gain is basically going to be given as follows. So we basically write as PE dot is FPE plus PE F transpose, and then we have a quadratic term here plus Q, and then what you can basically write this is that F is going to be the Jacobian, which is the derivative of F at the state estimates, and we can basically write this as follows. And then my LE, which is a gain that goes into the estimation over here, is calculated from PE. So essentially, you start with a PE at time equal to 0, and then solve this Riccati equation as time progresses, and you can actually estimate the L as time progresses. So this is going to depend on the value of F. So PE and L needs to be computed online. So this kind of adds to the computation cost of Kalman filter. So that's what gave us a faster response compared to the EKF. We wanted to do a more extensive comparison, so we wanted to put both the EKF as well as the equations we had before for the H infinity Riccati equations on the same basis, and then compare it for a Lipschitz nonlinear system. So just a quick cheat sheet. So any subscript which has either capital H or small h corresponds to the H infinity observer for the sector bounded case, and E or little e subscript denotes the EKF values. So if we define the covariance, the actual covariance rather than the Riccati equation matrices, we have the two systems, the extended Kalman filter and the H infinity filter, going as follows. So anytime you have a subscript S star, it denotes the actual covariance, and then the P is the matrix that's used to solve the Riccati equation. So when you notice that, we actually notice that in the EKF transients, if my A plus EJ minus LEC is Hurwitz, then the covariance P sub SE converges to the filter covariance, or put alternately, P sub SE converges to PE if and only if J equal to J transpose. For the H infinity transient behavior, the P sub SH remains bounded by PH from the solution of the Riccati equation. So the conclusion is that the EKF requires A plus EJ minus LE to be remain Hurwitz, which may not always be possible based on how the nonlinearity evolves. And then we also need we also see that the transients of the covariance of the H infinity filter remains upper bounded, so therefore it would be known as smaller. If you compare the steady state behavior, because we kind of do in the H infinity filter, we kind of look at the upper bound of the nonlinearity, my JPE plus PE J transpose is always going to be less than this term over here. So that means that the H infinity filter is going to have a larger steady state error. So we did again the simulation to compare the EKF with the observer, and then we noticed that, as we said before, the H infinity actually kind of both start off really badly. Notice that the EKF kind of continues to remain kind of oscillate till they actually converge, but then if you zoom in at the steady state, you will notice that the H infinity gets smaller error compared to the the EKF gives a smaller error at steady state compared to the H infinity observed. So if you look at it really closely, so this appears really strangely. So the EKF technically is an optimal observer, right? So you'd expect that the EKF would always be better performing than the H infinity observer that we have proposed. But what actually happens is that the H infinity observer is globally stable. So it can actually guarantee the performance all over for all values of X. So in particular, if my X and X hat are really far away when you start off, my H infinity observer potentially gives a better performance compared to the EKF, because EKF, the value of the phi doesn't actually match the value that's used by the EKF. So this actually gives a larger error, the EKF gives a larger error. So I just wanted to really quickly list some of the relevant publications that we have made in this area here. So in conclusions, we have provided an observer design for a very general class of nonlinear systems called as a generalized sector bounded nonlinearity. So the advantages compared to the EKFs and potentially the unscented Kalman filter is that the stability and performance is guaranteed globally. H infinity does not demand online covariance solution, since the Riccati equation is time invariant and it could actually be computed offline. So this makes it very efficient for embedded systems. So H infinity actually provides faster convergence of the error. This is particularly true when your initial estimates are further away, and H infinity actually tolerates much wider class of noises, and the LMI formulation for the H infinity provides a convenient solution. The main disadvantage of using the sector bounded, generalized sector bounded with the H infinity is that the EKF could potentially provide more accurate results at steady state, particularly if the noise statistics is known. So I'd like to acknowledge some of the contribution of my students who were and going to be joining the project. So Amir Vailabiji, who completed his master's with me. Sagar Mehta, who is very close to completing the project, so he's not working, so he's working on a different aspect of doing sliding mode observers. Ahmed Raza, he just joined for his PhD starting in summer 2017, so he's started working, kind of doing some optimization and then doing some results for existence condition. And then Hosseini Martina, so she's going to be joining us starting in fall 2017. So with that, I'd like to thank you for listening to my presentation. And then if you have any questions, please send me an email at krishna@sfu.ca, or you can post them in the YouTube comments. Thank you.